Beyond standard DSMB reviews for safety and data quality, there are interim analyses where you are actually looking at the endpoint or looking for efficacy data. You can also have stopping rules predefined for your study, and those stopping rules may be based on safety, such as if we see X number of events and the first N number of events will stop the trial. Both of those take planning and take some recognition of the overall alpha spending that you will have in your trial. So what is the purpose of an interim analysis? What are the pros and cons of them? And then what types of analyses are there? And what are the types of rules? So alpha spending rules, likelihood rules, and Bayesian rules are all used for interim analyses to stop a trial early. A quick review. Remember, when we set up our null and alternative hypotheses, the type 1 error is choosing the alternative when the null is really true, and so we attempt to minimize that. But your alpha is good for only one test. So how quickly does alpha rise if you don't control for multiple testing? Well, you can see very quickly the alpha will go up, or the family-wise error rate or the type 1 error rate will increase quite quickly with the number of tests that you perform on your primary endpoint. So the usual corrections we consider, say when we have an ANOVA and we found that there's a difference between our 4 categories or 4 treatments, we would normally adjust for multiple testing by using a multiple testing adjustment, like a Bonferroni, which, by the way, is too conservative for any more than 3 tests, because Bonferroni assumes that the tests are independent. But your null hypothesis is assuming that they all come from a similar distribution or the same distribution. So the assumption on Bonferroni is too restrictive. Tukey's HSD does not assume total independence. It is a better adjustment for multiple testing. But those generally won't serve you well for interim analysis testing. And why is that? Well, for the first thing is you have limited information, or at least reduced information, to make the determination at an interim analysis. The second reason is that when you're doing an ANOVA with a multiple testing, you're looking to see if it's same distribution versus different distributions. In an interim analysis, all of your participants come from your same sample area. And if you are using them to test the endpoint at time period T and then at time period T2, it's the same group of patients. In a standard multiple testing situation, we're attempting to divide the samples into separate groups. Here, we have the same set of patients every time we're doing the testing. So we'd be looking for evidence from a small amount of information to be overwhelmingly in favor of an alternative hypothesis, and simply doing a Bonferroni correction of 0.025 is going to be too lenient. The scientific community, of course, is more skeptical of results from small samples. Your trial was designed to find a reasonable difference, not an extreme or large difference. And so a large difference early on is going to be unlikely, especially with a larger standard error due to a small n. Using a larger alpha early will prevent you from detecting smaller differences later on. So if you are more likely to reject early, say if you're looking at weight loss, and you say, great, this 20-pound difference is statistically significant, well, that's not surprising. But what happens when you are looking at 5 or 7 pounds? And if you declare significance early at a 20-pound difference, you will not be able to declare significance later at a smaller weight difference. Common things to be aware of: lack of credibility, lack of realism, imprecision, and bias. So again, smaller n's lead to wider confidence intervals. Bias, this could be a local maximum, and more data would not represent the underlying response. Stopping early, of course, removes ability to assess full costs and risk-benefit profile. Strong early effects result in strong statements regarding results, and that may be overestimating the trial meaning. Remember, often in clinical trials, you're looking at prevalent cases where people may be worse, as opposed to incident cases where people may be more newly diagnosed. And longer-term follow-up and getting those incident cases may not reflect an early stopping result. And then, of course, you could be wrong. So there are mistakes made anytime that you can test an alpha And so you want to be really careful about not opening yourself up to make that mistake when you shouldn't be. So what do? So you need to figure out when and how many interim analyses will occur. You need to try to limit them. They do need scientific justification. And generally, this should be done before you start the trial. You can have interim analyses that are only for safety and do not spend alpha on the primary hypotheses. And if you meet the stopping rule for superiority, remember there could be other factors that result in the trial being continued. So looking for a longer-term safety profile, moving everyone from the standard of care or placebo arm up to this new active treatment and following them longer. So all of these issues need to be considered when you build in stopping rules for your trial. Likelihood methods are a fairly basic concept. They are better for quality control experiments, and this is a sequential method. So you would check the likelihood after each patient or set of patients has completed the endpoint, and you're simply creating a likelihood ratio. So what is, given the data that you have now, what is the likelihood that you'll end up at the null or likelihood that you'll end up at the alternative? And then you look at a ratio. Large ratios mean the likelihood is greater for HO. Small ratios mean the likelihood is greater for HA. And depending upon your specific alpha and beta, you'll then see a ratio upper limit and ratio lower limit. And once you have crossed a threshold, this study will stop. This is very easy to implement. The cons, however, is that you must be able to observe endpoints quite quickly. If you reach N without achieving RL or RU, then the trial will be inconclusive or often called negative. If you reach it early, then it could be very biased as well. Bayesian methods, the methodology is to specify the expected treatment difference, theta, define a distribution of theta, that's your prior, observe your data, that's your X. Again, likelihood based, the likelihood of X given your prior distribution, and then adjust the prior given X to get the posterior. Skeptical priors underestimate the treatment effect. Enthusiastic priors overestimate the treatment effect. The real one is usually somewhere in between, and you should definitely look at the spectrum from skeptical to enthusiastic. The stopping rules are based on the distribution probability observed after the posterior is determined. So you can see that there's a lot that goes into a Bayesian method for stopping rules, and that is, of course, the pro and the con. So it's a high level of statistical input. However, these are iterative estimations and they are computationally intensive. If the experimental treatment is new, you may not have prior, and then, of course, if you poorly select your prior, then everything is going to be off. The frequentist methods are much more common. They're dealing with the data that you observe. They have a more focus on type 1 error, and therefore these methods focus on controlling alpha. The common ones you'll hear are O'Brien-Fleming, Haybittle-Peto, Land-Demetz, or Demetz-Land. Pocock is an older method. We won't talk about it here. It is a simple fixed p-value at each look. The main con on Pocock is that the final test ends up way below your standard alpha. So you're actually spending alpha and not reaching your whole alpha limit with Pocock. So we will not talk about Pocock here. O'Brien-Fleming, first introduced in 1979, has had many adaptations since then. The maximum number of tests and the number of observations are considered between successive tests, and this needs to be fixed in advance. O'Brien-Fleming is a fixed procedure. O'Brien-Fleming is found to have virtually the same amount of power and the same amount of accuracy as a single sample chi-square test. It has been adjusted to control for type 1 error in the situation where there's correlation between the data and the time periods, which of course there obviously is, because the data you're using for your interim test will be incorporated into the data that you are using for your final test. It does require greater evidence of difference at earlier times. So if you see here for 2 total looks, your interim analysis and your final look, you would alpha test your interim at 0.005, and then your final test would be at a 0.049, so very nearly to 0.05. Frequentist tests are not additive like a Bonferroni with 0.05 divided in half. Because you have a relationship between the data you're using for your interim and the data that you're using for your full test, you can leverage that level of dependence. O'Brien-Fleming are relatively easy to implement, and they are conservative early when you have smaller data, which is what you'd like. They are, however, rigid in terms of the maximum number of pre-planned looks. So what if the trial ends early or fails to recruit the specified N? Then you have way overspent your alpha. Haybittle-Peto also came out in the 70s. This is going to adjust the critical value. So somewhat in the way that Tukey's HSD works, where it adjusts the critical value, not the alpha level. So you'll adjust the final alpha to achieve an overall alpha based upon this new critical value for Haybittle-Peto. So instead of a 1.96, for example, you would use a 1.98 or a 1.997 for a critical value here. Again, Haybittle-Peto is easy to implement. It does have constant stopping rules. So the final look will be near the overall level of significance, and you'll spend most of your alpha at the final look, similar to O'Brien-Fleming. Again, the problem with Haybittle-Peto is that they are very stringent, and it may be hard to stop early, and in that case, you've defeated the purpose of spending alpha. Alpha spending rules, first proposed by Demetz and Land in 1994 in Statistics and Medicine. The assumption that the information accumulated between each interim analysis is statistically independent. That does, however, have caveats and has since been amended. So Demetz-Land published in 94, Land-Demetz has been published later to update the need for statistical independence. It will also overcome earlier, more rigid rules, so you no longer have to have equal spacing between the scheduled analyses, because even recruitment is often unrealistic. And then you do not have to actually determine the number of analyses. They do not have to be fixed before the study. Land-Demetz actually looks at alpha as a function, such that at time 0, you've spent 0 alpha, and at time 1, the final time, you have spent all of your alpha. The basic concept is that the function at your specified time point, which is your information fraction, how much of your sample size have you collected, where are you, what is the time that you've hit, will actually be used to determine what your alpha level is for that test. So if you consider taking 0.5% of your information fraction, and that's when 50% of your patients have completed, you see it's based on the number of recruitments completed, not the time. So it's not at 50% of follow-up time, it is 50% of patients completing. At 0.25, so if you're looking at 25% of recruitment, then you would use an alpha of 0.0125. Alpha spending pros and cons, they are much more flexible sequential procedures. They don't require the total number nor the exact time of the interim analysis to be specified in advance. So if you decided to conduct an interim analysis at 0.7% information criteria, you could then figure out what your alpha level would be. Land-Demetz, again, was extended in 94 to look at longitudinal mixed models where incremental data is no longer required to be independent. What are the general issues with early testing? The estimates of a treatment effect are going to be biased when a trial is terminated at an early stage. You went through a lot of careful planning on your study to incorporate a number of considerations, and when you stop early, those assumptions no longer apply. The earlier you make the decision, the larger the potential bias. So think about if you have an interim with 180 out of 200, that seems to have more weight behind it than making a decision out of 25 people based on 200. So what do? You need to evaluate the broader context for your trial. Do you need an interim look? And it shouldn't simply be out of curiosity. A very common interim look is to plan a single look requiring a very large effect size. That allows for the DSMB to get a look without spending too much alpha. It also allows you to assess your effect size and your standard deviation assumptions, and that can be very helpful. Consider the expected early outcomes. So again, one of the big considerations is prevalent versus incident cases. The reasons you would need to stop early: if everyone is being treated with acceptable medications, there may be no justification. If you do not have a placebo arm and everyone is receiving at the minimum standard of care, stopping early may not be a reasonable consideration. If the reason that you're taking this interim look is because recruitment has drastically slowed, then it may be worth it to spend that alpha to determine if you can even completing your recruitment would get you to your pre-planned numbers. And then really utilize the DSMB as your experts to discuss the cons and ethical issues of stopping the trial early.